So we can start. Okay. In the previous class, we have seen about the determinant and trace criteria to show the stability of an equilibrium point, whether the equilibrium point is stable or unstable, based on the sign of the determinant and the trace. But it works for a 2x2 dynamical system. So when the dimension becomes more than 2x2, just if it is exceeds a 2x2 matrix. So we cannot use a trace and determinant. So we need more advanced criteria to show the stability of the given dynamical system is stable or not, in order to find the sign of the eigenvalues of the Jacobian matrix. So the one possible way of showing is using Routh's theorem or criteria. And this method is used to determine the stability of a linear system by analyzing the characteristic polynomial of the system. The key point here in the Routh's criteria is to count the number of poles or roots of the characteristic polynomial that lie in the right half plane of the xy plane, which corresponding to the number of poles with positive parts. If we can find an eigenvalue on the right half plane of the xy plane, if we can find, like, if we consider this one as an xy plane, the roots of the dynamical system, the eigenvalues of the dynamical system should lie on the other planes except this one, on the right half plane of the xy plane. If it lies on the right half plane of the xy plane, then the eigenvalue becomes positive. So we are required to find the coefficients of the characteristic polynomial should be positive in order to say that the given dynamical system has a negative eigenvalue for the corresponding equilibrium point. And if we get positive coefficients for the characteristic polynomial, we can say that the eigenvalues are negative, and we can state something about the stability of the equilibrium point, which means the equilibrium point is stable if the eigenvalues are negative. So the Routh's criteria provides a method to check if all the eigenvalues of the system have negative real parts without explicitly showing or solving the exact solution of the given system of differential equation or model or dynamical system. So by examining the Routh's matrices and their determinants, we can determine the stability of the system without explicitly finding the roots of the characteristic polynomial. So it provides the necessary as well as the sufficient condition for all roots of the characteristic polynomial to have a negative real parts. So what we do here is that after finding the Jacobian matrix, the Jacobian matrix is obtained from the nonlinear system by linearizing, and then linearizing the nonlinear system, we got a Jacobian matrix, and from that Jacobian matrix, substituting the eigenvalues, we get the matrices. That matrix is a matrix of constants, and then we can find the eigenvalue for that corresponding matrix. That eigenvalues are obtained from the characteristic polynomial, and assumes that we have an n by n system of differential equation, and so the characteristic equation has a polynomial degree of n of the form like this one. It has of the form like this one, p of lambda, which is equal to lambda to the power of n plus a1 lambda to the power of n minus 1 plus like that, and the last term is a constant term which is equal to 0. So the fundamental condition is that the Routh criteria shows the local stability of the equilibrium point by showing the eigenvalues are negative. It shows only the local stability, not the global stability of the given equilibrium point. So before applying the Routh criteria, one must know or build an array based on the in order to check the necessary conditions. What are the necessary conditions to apply the Routh criteria or build an array? Is that one, all the coefficients of the characteristic polynomial should have the same sign, usually positive. They should have the same sign or they have positive signs. All the coefficients should be positive. Two, all the coefficients must be non-zero. No missing powers of the lambda. No missing powers of lambda. There should not be a missing power in the what is just taken as a warning is that the coefficients should not be zero or negative. If we get a zero or a negative coefficient, the system is unstable immediately or marginally stable. So you do not need to proceed to the array building procedure or matrix building procedure if we have obtained negative or zero coefficients of the characteristic polynomial. Directly we can say it's an unstable equilibrium point. But we can check by going further looking the positivity of the coefficients. So according to the Routh criteria, we can define from the if we can define different Routh matrices where I is the order of the characteristic polynomial. Order of the characteristic polynomial. It's I is the order of the characteristic polynomial. If the characteristic polynomial is order 1, it's just 1 by 1 matrices, which is A1. If the characteristic polynomial is order 2, which is quadratic, we can write A1, 1, A3, A2, which is the 2 by 2 if the characteristic polynomial is quadratic. And if it is a cubic polynomial, then we can write the Routh matrix A1, 1, 0, A3, A2, A1, A5, A4, A3. So just if it is an n characteristic polynomial, so the n's Routh matrices is written in just in this way: A1, 1, 0, 0, A3, A2, A1, just like that, 0, then up to AN, so which is an n by n matrices, provided that AJ is 0 if J is greater than the order of the matrix. J is greater than the order of the matrix, where n is the order of the matrix. The order of the polynomial. N is እዚህ ጋር I ያልናት ማለት ነው። n ብላ ምን ያልናት እዚህ ጋር ካራክተር እንትኑ ጋር ማትሪክስ which is the order of the characteristic polynomial, which is how the degree of the characteristic polynomial, we can say. For instance, if for a polynomial function of degree 2, for a polynomial function of degree 2, lambda square plus a1 lambda plus a2, have you seen? So A3 is greater than a 2 by 2 matrix, so its value is 0. Its value is 0. So for a 2 by 2, for a characteristic polynomial of degree 2, it has of the form this one. So A1, 1, 0, and A2. It should be in such a way. So all roots of the polynomial have the negative real parts if the determinants of all the Routh matrices are positive. Have you seen? The eigenvalues are the roots of the poles of the polynomial function are negative. They have negative real parts, or they are negative. If they are real number, they are negative. If and only if all the determinants of the Routh matrix are positive. For instance, if we take the case of n is equal to 2, as we have seen it before, if we take this one, a 2 by 2 matrices, if we take this one, you can see that A1 is greater than 0. The coefficients should be A1 should be greater than 0, A2 should be greater than 0. And the other one is the determinant of H2, which is A1 times A2 minus A3. But A3 is, because A3 is, 3 is greater than the degree of the polynomial function, greater than 2, which is 0. It is 0. So that A1, A2 is greater than 0 is another condition. So if A1 is greater than 0 and A1 times A2 is greater than 0, so we can say that the degree of the coefficients of the quadratic polynomial are positive. Positive, it means that the Routh matrix have negative real part eigenvalues, and this negative real part eigenvalue indicates that the equilibrium point is a stable equilibrium point. The stable equilibrium point, and that stability is said to be local stable equilibrium point. So you can compare this one 2 by 2 matrix with that of what we have determined last time. For a 2 by 2 matrix, if the determinant of the Jacobian matrix is greater than 0 and the trace is the trace of J is less than 0, then we can say that we can say that the eigenvalue is a stable equilibrium point. You can say. We have said this one, I think. If the coefficients are greater than A1 and A2 greater than 0, the eigenvalues are negative, which means the trace is negative. The trace is negative. If the coefficients are positive, the trace is negative, and the determinant is a product of these negative values, which is positive. So it's equivalent to the trace and determinant concept. But if the degree of the polynomial function is higher than 2, then we should use the Routh criteria. We should use the Routh criteria. For instance, if it is 3, all the coefficients should be greater than 0. It's the first one. And in addition to that, A1 times A2 should be greater than A3. A1 times A2 should be greater than A3, or we can say A1 times A2 minus A3. We can say A1 times A2 minus A3 should be greater than 0. We can say this one, A1 times A2 minus A3, which is greater than 0 below. Consider now. So if each of the elements A1, A2, A3 should be greater than 0, and A1 times A2 minus A3 should be greater than 0, is we can check these two conditions, and then we can say that the equilibrium point is a stable equilibrium point. I think who is what's up? Is there any problem? Isa ba yan? Mute. Okay. 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 So the next is okay. Center arguten የእናንተውን ኦዲዮ ነው። So for the case of the polynomial function of degree 3 is of, these are the sufficient conditions that we should satisfy, that should be satisfied. For the case of n is polynomial degree 4, if the characteristic polynomial is degree 4, each ai should be greater than 0 and satisfy this condition. Should satisfy this condition. A1 times A2 times A3 should be greater than A3 the whole square plus A1 square times A4 should be greater than A1, A2, A3, the product A1, A2, A3 greater than A3 square plus A1 square plus times A4. And if it's a degree of polynomial degree 5, each coefficient should be greater than 0, and it should satisfy two conditions, this condition and the other one condition. there's one condition, two conditions should be satisfied. So in such a way, we can prove the given equilibrium point is whether it's locally asymptotically stable or not using the root rules criteria. So the necessary but not sufficient condition for roots of a polynomial function p lambda to be negative or have negative real part is that all the coefficients be strictly positive. Have you seen? It's necessary but not sufficient, because we should show also the additional conditions to be sure that the eigenvalues are negative. For instance, you can see this paper, which is mathematical modeling with optimal control analysis of social media addiction, which is done by Nagasa and me. And we considered an SEIRQ model, an SER, an SEI, which is A is just like I, R model, and Q is just like a quarantine. Those who are denying or accepting the using social media. So we consider that one, and it's developed by the system of differential equations in such a way. And solving, we obtained the social media free equilibrium point at this one. The social media free equilibrium point at this one. From that, to check the stability, the local stability of this social media free equilibrium point, to be whether it's stable or unstable, it's locally stable or unstable, we should find the Jacobian matrix. We should find the Jacobian matrix in such a way by finding the partial derivatives with respect to each state variables, with respect to S, with respect to E, with respect to A, with respect to R, and with respect to Q. So we got, after evaluating the Jacobian matrix at this free equilibrium point, we obtained this Jacobian matrix. So let's determine the eigenvalue for this Jacobian matrix. You can see that have you seen the first column? Below the pivot element, all are 0. Therefore, we can say that minus mu is the first eigenvalue. Minus mu is the first eigenvalue. And the other one, we reduced 5 by 5 into 4 by 4. And from this one, you can see this pivot element. And above it is 0, so that the other eigenvalue is minus mu also, which is the other eigenvalue, which is negative. Lambda 1 is negative and lambda 2 is negative. You see, look, our target is to, if the eigenvalues are negative, if all the eigenvalues are negative, then we can say that this free equilibrium point, or the social media the free equilibrium point, is a stable, locally stable equilibrium point. But we have not finished that. We got two we get two eigenvalues which are negative, but there are remaining 3 eigenvalues from the reduced one. So we have this reduced system, 3 by 3 system. So finding the characteristic polynomial for this 3 by 3 system, we obtain this polynomial function. We obtain this polynomial function. And the coefficients are these ones. A1 is this one, A2 is this one, A3 is this one. So what's required from us is that we should show that each AI should be greater than 0. In addition to that, since it's a 3 by 3, A1 times A2 should be greater than A3. We should show these things. Clearly, you can see that A1 is greater than 0, as you can see, because the parameters are all positive. But we don't know about A2 and A3. In this case, we use the reproduction number, the basic reproduction number, and rearrange or rewrite A1 and A3 in terms of the basic reproduction number, and check the positivity of the A2 and A3 in relation to the basic reproduction number. So that if the characteristic polynomial satisfies this condition, which means that the remaining 3 eigenvalues are negative. So if the remaining 3 eigenvalues are negative and these 2 eigenvalues are negative, then we can say that the social media free equilibrium point is locally asymptotically stable. So this is how to use practically the Routh criteria for if we cannot directly find the eigenvalues of Jacobian matrix, and then we can calculate the characteristic polynomial, and based on the degree of the characteristic polynomial, we can use the Routh criteria and checking the sufficient and necessary condition for the Routh criteria. We can say whether the equilibrium point is positive, equilibrium point is stable or unstable. Okay. So all the roots of the polynomial function, the polynomial P of lambda, have negative real parts, or it's said to be stable and locally symptotically stable if and only if the determinants of all the Routh matrices are positive. Mathematically, we can just we are looking that one. But we can also use the other way, or we can use Routh array in order to determine the sign of the sign of the eigenvalues, which is also the same to the matrix form, but this one is by using an array, constructing an array of Rouths. So we have a polynomial function, a characteristic polynomial, which is obtained from the Jacobian, and then we arrange in rows based on the powers of S. We arrange the rows based on the powers of S, like this one. So the SN rows are arranged AN, then AN minus 2, then AN minus 4 by jumping 1, 1. Then here the next one is AN minus 1, jumping AN minus 2, then AN minus 3, then AN minus 5. So we arrange the characteristic polynomial in 2 rows. We arrange the characteristic polynomial in 2 rows. Then the remaining rows are obtained from the characteristic polynomial coefficients. The characteristic polynomial coefficients. For instance, to determine this one, we use this one as a pivot. We use this one as a pivot. B1 is obtained by multiplying AN minus 1 times AN minus 1 times AN minus 2 minus AN times AN minus 3 over AN minus 1. Have you seen this? Which is B1 is obtained AN minus 1 times AN minus 2 minus AN times AN minus 3 over A1, AN minus 1. Similarly, B2 is obtained AN minus 1 times AN minus 4 minus AN minus 5, AN times AN minus 5 over AN minus 1. You can see B2 is obtained just like this one. Have you seen? Similarly, B3 is obtained like in such a way. And to determine C1, we use the pivot as B1 as a pivot. We use B1 as a pivot. So B1 times AN minus 3, B1 times AN minus 3 minus B1 times AN minus 3 minus AN times, AN minus 1, AN minus 1 times B2 over B1, which is C1, which is equal to B1 times AN minus 3 minus B2 times AN minus 1 over B1. C1 is obtained like this one. So each row uses the 2 rows immediately above it. So to determine each row, we use the 2 rows immediately above it, and we construct the Routh array. We construct the Routh array. So this is just the workflow for using Routh criteria in applying for a given Jacobian matrix or a given model. I think this one is a workflow. If we have obtained, if Routh criteria satisfies the property of the local stability, then we can say the equilibrium point is locally asymptotically stable. Now, what we do is that after constructing the Routh array, the number of roots with positive real parts, which is right hand half plane, from the right half plane, is equal to the number of sign changes in the first column of the roots array. Have you seen what that means? For instance, the equilibrium point is said to be, the stability of equilibrium point is said to be stable if, just like this one, if there is no sign change in the first column. If there is no sign change in the first column, if there is no sign change in the first column, then we can say that the Jacobian has a negative roots. The Jacobian has negative eigenvalues, which means the characteristic polynomial has negative roots. So if there is no sign change, we can say that it's locally stable. If there is a change, have you seen here? Plus, plus, negative, plus, which is unstable because there are two changes, from positive to negative and from negative to positive. There are two changes, which means that there are two roots in the positive half plane of the xy plane. There are two roots that lie in the first, there are two eigenvalues that lie in the first half plane of the xy plane, which means the equilibrium point is not stable. The equilibrium point is not stable. So we check the first column of the array, the rooters array, so that we can say that the equilibrium point is whether stable or unstable depending on the first column sign. If there is a change, sign change, from positive to negative or from negative to positive, then we can say that there is one positive root that lies in the first half plane, so that we cannot say the equilibrium point is stable. For instance, we have this characteristic polynomial, which is degree 3, and determine the value of k so that the roots of the characteristic polynomial are negative. The roots of the characteristic polynomial are negative. So we look only, we put the, since it's the characteristic polynomial is, we sit here, which is degree 3, degree 2, degree 1, degree 0. We, as a column, we sit, and the first two are obtained from the characteristic polynomial. So an is 1 here, an is 1 here, so 1, then we jump 1, and then the power of a1 is, which is degree 1 is a2, and the next one is 3, and jumping 1, which is k. After that, this is obtained by 3 times 2 minus 1 times k, which is 6 minus k over 3. And the other one is 0. The next one is this one, taking this 6 minus 3k as a pivot, which is 6 minus k over 3 times k minus 0 over 6 minus k over 3. Is that not? So 6 minus k by 6 minus k are cancelled. They cancelled each other. So what's left? Which is k is left. So we can see that for the characteristic polynomial to have negative eigenvalues, the coefficients of the first column should be positive. This first column value should be positive, which means that k1 should be positive 1, and the other one 6k minus 6 minus k over 3 should be greater than 0. So we have k1 is greater than 0, 1, and 6 minus k over 3 is greater than 0, means 6 minus k should be greater than 0, which means 6 should be greater than k, which implies k is less than 6. 0 from the first one, k is less than 0 is less than k less than 6. K should be between 0 and 6 to be, for the equilibrium point to be stable, or for the characteristic polynomial to have a negative eigenvalue, a negative root, or a negative pole. The k value should be between 0 and 6. The k value should be between 0 and 6. So this is how to find the stability of the characteristic polynomial. So So then you can take this example also, which is a polynomial function of degree 3. Characteristic polynomial is this one after linearizing. And the necessary condition is to check all the coefficients are positive. You can see 1, 6, 11, and 6, they are all positive. So they passed the first criteria. The Routh array, you can construct the Routh array, which is degree 3, degree 2, degree 1, degree 0. And then on this coefficient, you will put this one, and then one jump, and then you write 11, and you just take, and the other one 6, and one jump, and the other one 6. So to find this one, to find this value, we use this one, 6 times 11 minus 1 times 6 over 6, which is a pivot. So which is 10. The other element is 0, because here we have 0 elements. Here we have 0 elements. And the next one is to find this one. To find this one, we take this one as a pivot, then 10 times 6 minus 6 times 0 over 10, which gives 6, So you can see that with this one is positive, this one is positive, this one is positive, this one is positive. So there is no sign change in the first column, no sign change in the first column. Since there is no sign change in the first column, the polynomial has no roots in the right half plane, meaning that the equilibrium point is asymptotically stable, which means the roots of the characteristic polynomial are negative. The roots of the characteristic polynomial negative implies that the equilibrium point is locally asymptotically stable. For instance, you can check this one. You can take this one. What is the necessary condition? The coefficients. You can see A0 is negative. So what's our observation? The constant term A0 is negative. So what's our immediate conclusion? Because not all the coefficients have the same sign, the system is unstable. And we proceed that we Routh array to find the number of unstable roots. Have you seen? Directly, it's unstable, but we can check whether the first column shows a sign change or not by using the Routh array. We can show by using the Routh array, we can show whether it's root the sign is there is a sign change or not. So as you can see, I think it shows step by step the procedures that you follow. The first one is the characteristic polynomial stated as this one, and then we can find the first one here. You can see 1 is 1 times 3 minus 1 times 2 over 1, which gives 1. Similarly, 5 is obtained 2 times 1 times minus 5, 1 times minus 5, 1 times minus 5, and 1 times 0 over 1, which is minus 5. 1 times minus 5 minus 0 over 1, which is minus 5, is that not? We obtain this one. The other one is 0. The next one is this one. This is obtained. So always when we are looking this to find this row, we use immediately the above 2 rows. So this one will be the pivot. So 1 times 2 minus 5, so which is 1 times 2 minus 1 times minus 5 over 1, which is 2 plus 5 over 1, which is 7. You get this one 7. The other one has 1 times 0, which is 0, over 1 minus 1 times 0, which is also 0, over 1 is just 0. And this element is obtained immediately using this one as a pivot, 7 as a pivot. 7 times minus 5, 7 times minus 5 minus 1 times 0 over what? Over 7, which is minus 5, Now you can see there is a sign change in the fourth and the fifth row. In the fourth and the fifth row. So what? There is one root which is found in the positive half plane of the xy plane, which means all the eigenvalues of the characteristic polynomial are not negative. All the characteristic polynomials of the are not negative, which means the equilibrium point is not stable. Directly, we have obtained from the necessary conditions, checking the coefficients, we have checked that they are not all positive. The coefficients are not all positive, so that it's not stable. And from the table, I think we have put the necessary and sufficient criteria. All the coefficients first should be positive. All the coefficients should be positive to apply the additional rules of the Routh criteria. So checking the coefficients are positive first is the first criteria that should be done before applying the Routh array. Before applying the Routh array. So this is how to check the Routh how to apply the Routh criteria. I think the other concept is bifurcation. I think you have learned about this thing, so I do not want to touch. But roughly, I was looking over, but it is not well constructed. I think, I think ይሄን ነገር ተምራችሁታል. I think topics in differential equation or somewhere, or ይሄን ነገር እስኪ እዩት እናንተ በደንብ። እኔ እንኳን አይ ቲንክ በደንብ አላየሁትም፣ በደንብ እንትን አላልኩትም። ኦልሬዲ ሌክቸር ኖታችሁ ጋር እዛ አንደኛው ኮርስ አውት ላይ ስላለ ትቼዋለሁ እንደ በፍሪኬሽን ኮንሰፕት ኦር ሞር ፋርዘር እዛ ጋር በደንብ ማየት ትችላላችሁ እናንተ። እኔ ላዘጋጀው ፈልጌ ነበረ but I have seen that there is a content on the topics in differential equation and dynamical system ላይ, so I left it. So I think for this section, it's enough to use this link, and let's change our link to the other link. Thank you. If you have a question in the time, if that's time, you can say something. እሺ yeah. Yeah. positive ስለሆነ exactly. Yeah. ያ ኤግዛክትሊ። አሁን እኛ ስለ ፓራሜትሮቹ ብዙ ጊዜ እንዳያቸው ቅድም እንዳየነው ኤግዛምፕሉ ላይ እንዳመጣሁትኝ እዛ ጋር we don't know about the sign of the parameter። እዚህ ጋር እንደምታየው አሁን እዚህ ፕሮፐርቲዎች ላይ ከኤ1 ውጪ ኤ2 እና ኤ3 we can't decide whether it's positive or negative አይደል? So that's why basic production number 1 እዚህ ጋር ብናመጣት are not less than 1 ምን ይሆናል? እነዚህ ኤዎችን ክራይቴሪያው የምናመጣው ለዛ ነው። እና እንደዚህ ደግሞ ቁጥር አይደለም አይሆን እንደዚህ እስከ መጨረሻው ድረስ መሄድ አለብን። ፖዚቲቭ ነው ኔጌቲቭ ነው ማለት ይሄ ኮኤፊሽንቱን ፈርስት ኮሎመኑን ማየት አለብን። ጥያቄ ነው መቀጠል ይችላል። እንዴ በመሀል አቋረጥኩ መሰለኝ። እሺ ኤግዛክትሊ ኤግዛክትሊ ጀስት እንዴት ማኑዋሊ አፕላይ እናደርገዋለን ነው። ብዙ ጊዜ ማትመጠን የሆኑ ነገሮች ወረድ ብለው በኢዚሊ በሆነ ነገር እናያቸውና በኋላ ኮምፕሌክስ ላይ አፕላይ ስናደርጋቸው ዘ ሴም ፕሮሲጀር ነው ፎሎ የምናደርገው፣ ግን እንደዚህ ቀላል አይደለም።